our last presenter in this section is Rex Alexander. He is with 5 Alpha LLC, co-founder and president. He's a 40-year veteran of aviation. Alpha LLC is a globally recognized aeronautical consultancy specializing in helicopter and vertical flight infrastructure development, safety, training, and education. Rex currently serves as infrastructure advisor to the Vertical Flight Society. He's co-chair of the U.S. Helicopter Safety Team's Infrastructure Working Group and is a committee member on the National Fire Protection 418 standard for heliports. He's past president of National EMS Pilots Association and past president of the Indiana Association for Air Medical Services. He's an alumnus of Parks College of Aviation at St. Louis University and a former U.S. Army Warrant Officer and Aero Scout helicopter instructor pilot, having served both on active duty and in the Indiana National Guard. Please welcome Rex.
Well, thank you again, Yolanda, for the opportunity to come in here and speak today. It's greatly appreciated. I'm the blue-collar guy. I'm the guy that actually goes out there and flies the helicopters with 33 years in military and offshore, and the bulk of that was 20 years in EMS. So in experiencing that, working in infrastructure came around, somebody goes, how did you wind up in that niche market? I said, there just came a point in time where I kept wondering why architects and engineers were trying to kill me in any given day. And it wasn't because they were bad people, it's because they didn't know what they didn't know. So out of that was born a company. We started doing a lot of education on what infrastructure was. And a lot of people think of infrastructure as a two-dimensional quantity, whereas it's a three-dimensional quantity where airspace is attached to it and it's affected by its environment significantly. And how you design it can have a huge impact on your safety and your performance. And we have a saying is infrastructure should not try to kill you if you blink. And that's one of those things. We try to build forgiveness into anything that we design. Right one? All right. So one of the things we design to is what we refer to as a design aircraft. And this comes from the Federal Aviation Administration's guidance in the advisory circular for heliports. The design aircraft in a helicopter is somewhat simple because it's based on max rotor diameter and max overall length. Our challenge today is what is going to be the design aircraft. And at last count, this is a couple weeks ago, working with Mike Hirschberg and the Vertical Flight Society, we were at somewhere in 175 different prototypes in this space. So figuring out what this is going to be, it doesn't have a main rotor, so it's got a lot of little rotors. Sometimes 3, sometimes 6, sometimes I've seen some really interesting numbers. The overall width is a lot of times greater than the overall length. Okay, so trying to figure out what that means with the FAA and working with them, one of the key factors that they're looking for is performance data, because that's what they use to base their current standards on. Well, we don't really have any performance data to work from yet. So they actually put out an RFI in April. I think it's got a suspense date of the end of this month on asking for help from OEMs and the like on creating this performance data. So that's what we have to have before we even go to square one on what the design looks like. So what we're basing a lot of what we have on today is what we currently have in infrastructure today. When we look at infrastructure, we have airports and heliports. We're looking, and I use vertiport, that's the most common term. I've heard a bunch of different terms out there, but vertiport's the one I'm going to use. So airports, we pretty much figure that everything's going to be operating at an airport. You have the room to land a helicopter there, jets, turboprops, and we expect vertical lift and takeoff vehicles to land and operate there too. Heliports, the assumption is that helicopters and probably vertical takeoff and lift aircraft, depending on the standards that we come up with, will operate there. Now, I'm getting a lot of calls from investors on, hey, I have this heliport, I want to make it a vertiport, what should I look for? It gets a little more complicated than just a piece of property somewhere. You have a lot of different layers you have to go through. Then the vertiport, we haven't really decided exactly what that looks like. Personal opinion, it's going to look very similar to a heliport with some minor nuances. Now, the key question is here, when we look at all the things that are going on in this industry today, specifically around the idea of some of the things we see on video, these wonderful animations. or even some of the vehicles that are actually flying today. And you see these tests. You see them in a pristine environment at an airport with lots and lots of room. Now, having worked in the other world, rooftop versus ground, a lot of the work I do is up on buildings. And it's a whole different environment. And we have to take into a lot of considerations in that environment to be able to build something that's going to be safe. So the answer is, are these equal? Yes and no. On the ground at airports, yeah, it probably is. But once you go on the roof, and once you start to look at that environment, all bets are off. Now, key performance criteria, we look at helicopters. So I'm going to kind of look at what we deal with today. So pilot workload is a big one. How much work is the pilot doing to keep that aircraft under control? Now we look at autonomous aircraft, how much work and how can the computer keep up with that? Probably better than the pilot can in many cases, but that's something we have to factor in. Handling and controllability characteristics. Some aircraft are better than others. I've flown many aircraft that deal with these environmental issues better. Also, training and education and knowing what you're getting into before you get into it has an impact on this. Aircraft performance margins. How much do you have before you over torque or over temp the aircraft? And I've seen bad infrastructure cause this to happen quite often because the pilot was asking more from its aircraft than it was capable of providing that given day. And then the passenger ride quality. So this is one I'm working right now with NASA Ames on with PK's folks. And the idea is you don't want passengers getting off your aircraft with a six-sack in their hand every time or they're not going to come back. So we're actually creating infrastructure and doing simulations on what this looks like and what can this vehicle actually do and what can't it do in this infrastructure. Now, one of the things, this came up like about a week ago, we talked about weight and balance. So in weight and balance in the aircraft today, flying EMS and some underpowered aircraft, one of the pieces that we had that we could play with on any given day was the fuel. So volume of fuel can be manipulated, battery volume is fixed. And this became really, really important for us because on any given day, if it's a nice cold day, you can carry more weight. On a nice hot day, you can carry less weight. And we had this saying in EMS, I can carry one of two things. I can either carry ass or I can carry gas, but I can't carry both. So you have to balance that. And there was many, many times that we would have to keep our fuel down to a lower volume. And if we got a really long flight, we would add fuel for that. But if we got a really short flight, we would have to keep it really low because we knew we were only going to go 6 minutes out. We wouldn't be able to take off given the performance values of that particular aircraft. And some of the other things that we get into that, turbulence and winds also have an effect. So weight and balance during flight. With fuel, it's always changing. So the weight and balance envelope's constantly moving. What we're looking at here is weight and balance envelope. Not going to change that much. You're going to land and take off with pretty much the exact same weight. That's good and bad in some cases. What we look at is the landing max gross weight. Are we going to put these aircraft to land at max gross on every given edition? If it's a 7,000 max gross aircraft and I fill all 4 seats, I have no manipulation now of the fuel. What's that look like for landing? And there's a lot of times we can take off with less weight in a helicopter. We can land with more weight. And it's all about can you hover. In the Gulf of Mexico, when you're taking off from a rig, the rule of thumb was if you can achieve a 3-foot hover, you could take off. Now I saw a 412 try to take off from a rig that could achieve about a 1-foot hover, and when he got out of in-ground effect, he disappeared. He got into ground effect over the water, and we watched him for about 4 miles until he finally achieved a climb. That was like, yeah, he probably had to go home and change his underwear. So these are some of the factors that we deal with, but we can manipulate weight by fuel. In EMS, you never knew what you were going to get into. A lot of times you'd show up and they said, oh yeah, the patient weighs 200 pounds. You walk in the door, so they haven't seen 200 pounds in 10 years. And if it was a short flight, it was routine, land, drop the crew, go fly, and burn fuel off. and then come back and land so you could come out of that hole. So now in this, I don't have that factor. Now we have to be very, very cognizant of the performance capabilities of these locations we're going to go into. So environmental factors, winds, we talk about crosswinds and tailwinds. Tailwinds we want to avoid. Crosswinds we need to be able to account for. We always like to land into the wind whenever possible. Turbulence, updrafts and downdrafts, we've got to be able to compensate for. Power margins, we want to have control, compensate for anything that hits us, and then overcome that. Those are the things we look for. And there's sometimes the helicopter can't do that. And I've been in those environments where you had to fly out of it or fly away from it or just don't land there because you can't overcome that. So it's not a safe situation. So this is a video of a helicopter landing on a heliport that was poorly designed. This was put flat on the roof. And that's the last thing you want to do with a heliport is put it flat on the roof. You want an air gap for air to flow under. So in this case, this pad was opened, I want to say for 4 days, and we destroyed an aircraft on day 4. We had 5 incidents up there over a 4-year period. Aircraft comes in from the upper left. Pilot's trying to control it. He gets into a bumpy ride at the end, trying to get it on the ground. Wind's coming off his nose. It's about 27 knots based on the AWAS. This is on 9 floors up. He's trying to get it on the ground. He's trying to get it on the ground. He's trying to get on the ground. Finally, sticks it on the ground. So it's bumpy. Now, with that, this is shutdown. So I mark the blades in a static position. He's at idle, and he just shut the engine off, and he's in coast down. So the advancing blade is closest to you. The retreating blade is farthest away. These are the points that they move from to. If I can get this thing to cycle. So the advancing blade's going forward and drooping. The retreating blade is coming up. Wind, again, is off the nose. We get about a 6-foot deflection in the front. These blades are static at 9 feet. That's why I always tell crew members this: never ever exit an aircraft during shutdown. If you're 6'2", you may not be any longer. Now the retreating blade, as it comes past the tail boom, starts to droop. It goes about 5 feet 5 inches, we figured based on calculations. It's hard to see in that picture. That piece of the tail boom goes across the pad. Now this is a different accident. Blades came down, took out both vertical fins, separated the back end of the blade. Looked like a pita pocket when we got done. Again, this is one of 5. We almost cut the tail boom off of one aircraft. Now in New York, there was an actual NTSB accident where they actually did cut the tail boom off of BK-117 because of this problem. Turbulence. So the advisory circular that the FAA put out, they had done wind tunnel testing to identify turbulence in and around buildings. In there, they talk about a 6-foot air gap, clear air gap underneath the pad. Well, I tracked down the guys that actually did this, and they said they never really tested it. That was kind of a swag. So we actually have done a lot of wind tunnel testing, and this is a 6-foot air gap. We get a little airflow underneath the pad, but not enough to make the difference. What we're looking for is to get that air that's coming up the side of the building to go under the pad so the top of the pad is a nice clear laminar flow. In this case, we don't achieve that. We find that it's at least a 10 to 12 foot gap that's clear. That's why I lean very heavily towards parking garages, because they're usually perforated on all 4 sides, lend themselves very well to this. And a lot of the retrofits that we're looking for, I climbed around 30 structures in downtown LA for Uber, looking at what makes a good location. Most of them don't. When you get into this turbulence issue, most of them don't have the capability to add another structure. They're not structural integrity there to add more weight. So in a case like this, you can see where the different circulations go. And what we run into is, and I've rode this roller coaster many a times in my career, and I was fortunate. I'd never over-torqued or over-temped or bent an aircraft, but I had several friends who have. So in the headwind, you got good performance, and all of a sudden you get that downdraft, tailwind, updraft. So you're going through this cycle, and right about the time you get over the pad, you get this downdraft. and it will try, it's like we call it the hand of God trying to stick you into that pad. And one of the things I like about the electrification piece is when we look at the ability to have instant power. Turbines don't have that. When I pull that thing up really quick, it lets me know because it droops and lags. And its pucker factor goes up by an exponential point. If I had something that had that, all of a sudden the controllability would be off the charts. Now, if I was maneuvering it, I could see that the pilot might over-control in a case like that. So we need something to manage that. So this is a project we worked on in Chicago. Lurie Children's Hospital is one of the most, how would I say, contested heliports I've ever been on. But it's in downtown Chicago. So this is the definition of an urban canyon. So you look down here on the lower, oops, you gotta go back. Down there on the lower right corner, notice the windsocks all 4 point in different directions. All right? It is what it is. We actually put an AWAS 3 up here so we'd have information going to the pilot, because the difference between ground-based weather and rooftop can be significantly different. And they don't call it the Windy City for nothing. So we spent a lot of time modeling this. We worked with a company called RWDI. We miniaturized Chicago, put it in a wind tunnel. I spent some time with these guys, and we actually mapped out the airflow, looked for where are the problem areas, where are the issues we're going to run into, where do we need to avoid, where are the better places. So we then put in our approach departure paths for testing based on some of this information. Now, once we got done, we had to prove beyond a shadow of a doubt that this was safe, because we had a lot of people that didn't like the idea of doing this. So we outfitted a helicopter, a Twin Star, with I call it the poor man's flight data monitoring system, Perio C1000. Great product. They're actually here at the show. But we do in-cockpit recording of the cockpit itself, seeing what the pilot's doing. I was videotaping quite a bit from the right seat. We also have the capability of playing back in 3 dimensions, and then we have the telemetry that's it's picking up as far as your airspeed, ground speed, rate of ascent, descent, and all the G-forces that are acting on the situation. So we flew, should be sound. There we go. Not real good sound, but there should be sound. So we flew this 82 approaches and departures over a 4-month period in multiple wind conditions to prove that it could be done. Now, the key here is we knew that it wouldn't be able to be done under all conditions. There's an operational limitation in this case of 25 knots being the maximum. That's the cutoff point. Under that, we proved that we could do it safely. We had controllability. We had pilot workload was not excessive, and ride quality was good. And we got done, and we found places that we shouldn't go. And we tested it. We found some areas that were definitely areas you wouldn't want to fly through on a regular basis. It was a challenge. Yeah. So that was, like I said, one of the most over-tested heliports in the world, I think, as far as testing goes. Now, this was one of the latest ones I was involved in. This is the 1000 Museum in Miami, Florida, 65 stories in downtown Miami. Now notice in the illustration, all the windsocks are lined up the same direction. Artists have the capability of making it look right. Reality is not this, trust me. So in this case, we actually designed the heliport. Now, we were having a challenge we did the wind tunnel, but architecturally, we got into this issue of what was, quote, aesthetically pleasing. And I said, aesthetically pleasing is another term for really, really dangerous in the aviation world. So we mocked it up, same group, RWDI. We had a 5-foot, a 15-foot, and a 20-foot rooftop. And this is some of the video. This is doing the 5-foot test. And we pretty much knew where we were going to get. We were still getting that burble in that turbulent zone. And mind you, these guys wanted to fly single engine R-44s up here. Well, on a clear day, and you had, a little bit of fuel and only 1 or 2 passengers, doable. But in the slow motion, you can see where you start to really see that turbulence. It's going to push whoever goes through there towards that pad. Now, this one, this is the 20. You can see that it's actually getting underneath there pretty good. And we're not getting the burble that we're getting on the 5. So this is working, but the problem is it's not aesthetically pleasing. So they spent a lot of money on this building. It's designed by a very famous architect, and they said, no, we can't put it. So we had to put the operational limitation on it. So, okay, at 20 knots, 65 stories, and it's, it's a 60 by 60 pad up there, that's when you cease. So we put a wind speed indicator up there to make sure. And they were okay. They didn't want that ugly, pad up there 20 feet above it looking like somebody's top hat on the building. Now, in closing, I will say, if you build it, they will come, right? They don't tell you who will come. You don't know when you go through all this work, all this effort, all this research, what's the first thing they put on the pad? Sound? I mean, I spent a lot of time designing this for a helicopter. They put a friggin' Formula One car. It's cool as all get out. But they did donuts on my pad. It was impressive the work they did to get this thing up there. Somebody asked me, how'd they get that car to stay on the pad? That's where they drill a hole through the tire and drive this huge bolt into the concrete. And it just stays in one point. But it looks really, really cool. And I got to say, that's some of the best video of that pad ever shot was for that commercial. But in that lies kind of an insider's joke, is you never know what's going to show up at one of these heliports or one of these vertiports. And we have to be careful of where we design it to, what standard do we design it to, and you don't want to design it to the absolute lowest denominator, because we get into this issue right now, and this is one of those things we're working with the FAA, airports, and standards on, is heliports and vertiports into the future may be different in that heliports and airports currently are quantified as public use and private use. In so much you look at that, there's about a 65-35 split in airports. So 65 private, 35 public. Airports are totally different though. When you get to heliports, it's 1 to 99. There are 60 public use heliports in the United States. 99%, over 5,600 and plus, of known heliports, because there's about 16 to 1,800 that we find that are missing, are private use. And the key there is, while the FAA has guidance and recommendations and criteria, the FAA has no authority over private use facilities. So if we call these vertiports private use, there is nothing the FAA could ever do to step in and say, hey, you're not doing it right, fix this. They can't. They don't have the legislative authority to do that. So they're looking at a new category of maybe commercial use. We get into that area that becomes challenging at the policy level. So where that winds up, I'm not sure. But when we get into what then does the FAA have total authority over, then it goes to the AIP funding, Airport Improvement Planning. So I did the research. Up until 2017, there was one heliport in the US that used AIP funding that was a standalone heliport. There was 32 co-located heliports at airports, but they were rather large airports. So they had to meet. So there's one heliport in the entire US, an Indianapolis downtown heliport, where the FAA can say, you have to do it, and they have to do it. The other ones, it's just a recommendation. And we get into that operational piece. Part 121 requires a Part 139 certificate for the airport. And it has to be certified on an annual basis. Part 135.229 says 135 operator needs to be adequate. Well, that's kind of a subjective term. I could ask 5 FSDOs what adequate is in their mind and get 6 different answers. So it's a challenge when we're looking at what this infrastructure needs to look like. We get into the battery, the autonomous, the performance. Infrastructure can be a huge help, or it can be a huge hindrance. So it's like figuring out what this design looks like, working with NASA and working with the FAA, I also sit on the NFPA, National Fire Protection Association, trying to get all those. The Vertical Flight Society is holding its workshop in September. This is a full day topic at the workshop in September. We're going to try and set as many FAA folks, NASAO folks, NFPA, International Building Code, International Fire Code, International Electric Code, in that room to have this discussion. We're not going to solve anything, but we're going to look at all the barriers, who owns the barriers, and then how we move forward. So that's all I have. So thank you so much. I appreciate it.